And Mr. Sadler.
And today we're going to continue to talk about momentum, but specifically we're going to talk about conservation of momentum.
Whenever we talk about conservation of anything, it's always, so that means conservation of momentum means momentum cannot be created or destroyed.
Correct.
So we got to find it somewhere.
So the change in the momentum is zero, or the beginning momentum is the same as the final momentum, or we can use words like initial instead of beginning. We can use words like final instead of end. So momentum is a conserved quantity. That is a fact. And I'm not really sure how we want to start this conversation, but
the picture on page 310,
Ooh, 310.
I thought was interesting. I asked the students in my class if they could tell me what the velocity was after the two carts crashed.
Well, that depends on some things.
It depends on some things, but I can guess. Looking at the picture, I can guess.
Sure. So momentum, if we recall from the other day, was P equals mv, dependent on mass
And velocity.
and velocity. It was a vector, which means the momentum and the velocity are in the same direction.
Mm-hmm.
So one thing I want to get across is that momentum conservation is a system, not an individual thing. So if momentum, if it was an individual thing, in a car crash, for example, the first car would finish with the same speed that it started with, and the other car would finish with the same speed that it started with, when in fact that's actually dead wrong.
Correct.
Right? What happens, of course, is that the momentum of one object is transferred to another object. So you talk about 310, and we see two roller coaster cars there, don't we?
Right, and they look similar.
They look about the same, don't they? So what we could talk about here, just if we were to use symbols, okay, is that momentum is in fact a conserved quantity, meaning that the system doesn't change.
Right,
That the total initial equals the total final.
correct.
And in the initial case, before the crash, so we are talking about the red car with the 1 on it, okay? That car, so we would say that the P of the red car would be equal to
The momentum of both
red
cars.
plus blue.
Correct.
Now, we can talk about the momentum of the blue car if you would like
In the beginning,
in the beginning,
but it's zero.
but it's zero because
There's no velocity.
it's not moving. Remember, momentum is mv.
Right.
Okay, so because of that, it has no momentum. So we get into the nitty-gritty of this thing.
But we're only excluding it because it's zero. If
Correct.
it did have some momentum, we could still do the same thing.
We could leave it in there and
Right.
cancel things out at the end,
Right.
but I like to get rid of stuff
Right.
if I can. We get into the nitty-gritty of this. We're going to talk about the mass of red times the initial speed of red
Mhm.
is equal to the mass of red times the final speed of red plus the mass of blue times the final speed of blue.
Right. But if red and blue are stuck together, then we know something about velocity.
Very good. So, if they're stuck together, aren't they just one giant object?
Correct.
And they're both roller coaster cars, so I'm going to go out on a limb and I'm going to say
That they're equal.
that they're equal, that the mass of red and the mass of blue, in fact, are identical. And so what ends up happening is you get m VIR is equal to, well, I do a little, what property of math is that? We'll have to look that up and put it on a call-out. But since they both have m terms that are exactly the same, I'm going to pull out the m term,
Right.
and I'm just going to add the final velocities. And something really nice starts to happen. Hey, look, I have m terms on both sides,
Mhm.
so the initial velocity of red is equal to the sum of the velocities of red plus blue.
Oh, very nice.
Now this only works because the masses of both objects are exactly the same,
Right.
okay? And because they're stuck together, actually, we know that they actually have the same velocity.
Correct.
So we can take it one step further. We can say that double the final velocity is equal to the initial velocity of the moving car, the red car.
So really, in this example, the velocity of the two objects is just half of the velocity of the one object.
That is correct. Anything above my blue line,
That one worked out really nice.
yeah, that was almost like we planned it.
Mhm.
Yeah. Anything above the blue line, okay, this is physics. Anything below the blue line, this is algebra.
Right.
Okay, so we keep having that conversation. The physics stops at some point and it just becomes math. Okay? This works for anything. This works if you are playing pool. This works in your car crashes that we do in the classroom with our little physics cars. This works in bumper cars. This were to work if we were to do problems with numbers. But what I really love about conservation, okay, conservation of anything, conservation makes things easier. Okay? What conservation is, we know that it means it's the same in the beginning and the
Correct.
end and all these other items. And if we just have to find it, we talked about conservation of energy, just find the missing energy. It's there somewhere.
Right.
Just find the momentum. It's there somewhere. Really, conservation is a problem-solving strategy. Well, can't spell strategy. And so this is something that I really want to emphasize because it's really important. I believe that covers conservation of momentum. We're going to break it down and do some problems and maybe derive conservation of momentum in the AP Plus podcast.
Right, and there are a couple of other problems in the regular
That
physics
we'll
talk
take a
that you
look
can
at
look
as
at.
well. Yeah.
Right.
So signing off, this is Mr. White.
And Mr. Sadler.